Welcome back to the next video, everybody. Today's video will be on a classification of certain representations and a little tiny glimpse of Carroll's hard theorem, which we talked about in the first two chapters of my series of talks. So first of all, it's going to be convenient for us to have a precise version of the classification of two-dimensional continuous semi-simple reps rho on the Weil group of F into GL2 of C, where F is a number field. So let's look at that classification. One quick definition first from representation theory. Let's let G be a group and let's let H be a subgroup of G. We'll let K be a field and we'll let pi be a K-linear representation of H. So I've got a representation on the subgroup. Well, that's the same thing as, you can also always view a representation like this as just a K bracket H module V, or KH is the group ring of H over V. Look, you can think of this as a group ring module, sure, but really what's going on here is you're saying V is a K module with an H action on it. That's how I like to think about it. Again, once you think about it like that, it's sort of obviously the same thing as the representation theoretic point of view. Okay, is there some way of kind of bumping this representation up to G, a representation of G? Yes, we can define the induced representation of G by H as ind GH pi. And what you do is you just take V and you tensor it up to the group ring KG. You just take V and you start thinking of it as a KG module, essentially, right? You think of it as a, this is just saying take V and think of it as a K module with a G action on it. And the natural way, that natural way is via the tensor product. That's what tensor products do, right? They let us think of modules as other modules in some sense. Okay, so what is this classification? Proposition 3, let's let rho be as above. So it's a representation from the Weil group of a number field F to GL2 of C. The image of rho in PGL2 of C is classified as one of the following three types. It's either cyclic type, which means rho is cyclic, which implies that its image is, it can be given by the direct sum of two one-dimensional representations. Okay, one-dimensional representations are characters, so we'll call them mu and nu. Okay. It can also be of dihedral type, which means the image of rho is, it's not cyclic, but it's dihedral. Well, what does that mean? What do you think it means? It means it's induced from a one-dimensional representation of an index 2 subgroup of the Galois group of G sub F, or I guess in this case, maybe W sub F. Okay, so that is, rho is monomial. Okay. Or it can be exceptional type, which means the image of rho in PGL2 of C is A4, S4, or A5 as a group. Okay. The proof of this follows from results in Enlica group in 1, chapter 2. Although the results there sort of state all this for representations of Galois groups, but if you kind of combined the result there with our exposition on Weil groups, you see that you can do the same thing for representations on Weil groups, W sub F. Okay? Okay, so let's switch gears for just a second. We should ask a relevant question now. If I give you a number field F and you assume LRC holds for all irreducible rho of the Weil group W sub F to GL2 of C, which automorphic cuspidal representations of GL2 of the Adels of F are of the form pi of rho for some rho? So remember, we have this representation pi of rho on the GL2 of the Adels admitted by LRC. But there's also just the entire class of automorphic cuspidal representations of this group. Which ones are of this form? Which ones are of the LRC or Artin form, let's say? Well, it turns out a necessary condition is given by the following definition. If I give you an irreducible admissible representation pi with local components pi sub v of GL2 of the Adels of F, and then a real place v, let's let rho sub v from the Weil group of C over R GL2 of C be the Langlands parameter of pi sub v. Okay, we'll say pi is Galois type, respectively arithmetic type, if the restriction of that local component, that Langlands class, to C star is just trivial. Or respectively, if it's the sum of characters of the form Z maps to Z to the A, Z bar to the B with A, B integers. Okay, so as an example, so if rho from the Weil group of Q to GL2 C maps through GQ, the Galois group, then if it exists, because we don't know LRC holds, pi of rho will be of Galois type. Why? Well, if you go back to my previous videos and you locate proposition 2 and do just a little bit of work, put a little bit of elbow grease into the situation, you get the result pretty quickly. And I'll say also that it's actually conjectured that all cuspidal pi of GL2 of AQ of Galois type actually arise in this way. They're just these representations that factor through G sub Q. Okay. When rho is odd, don't we already know this though? Yeah, we do. It follows from the Deligne-Serre construction given last video. So when rho is odd, this is actually known. So I should say a little bit about representations of arithmetic type now. The cuspidal pi of rows of arithmetic type turn out to be connected intimately with L-adic representations of the Galois group or Weil group of Q. You can see modular functions of one variable 2 for details. And it might be worth you checking into this, even though we won't really use it. It turns out to be a reformulation and even a generalization of Eichler-Shimura, which we did use in terms of representation theory. Okay, so that's pretty neat. I haven't actually looked into that myself, but I will be doing that. Okay, so let's take a little glimpse into Carriol's hard theorem, a mysterious theorem that popped up so many times, so many videos ago. I have a whole chapter on this theorem coming up much later, chapter 20. We're on chapter 6 right now, but in time we'll get there. But let's just take a little glimpse into it right now. Let's suppose rho sub infinity is induced from the character z maps to z to the negative n z bar to the negative m of c, with n bigger than m bigger than or equal to 0. And we'll take d sub k to be the discrete series representation of GL2R with lowest weight k equals n minus m plus 1, and then some suitably chosen central character that I don't want to describe right now. If you look in Langland's modular forms and L-adic representations, the author associates to each pi with local components pi sub v of arithmetic type with pi sub infinity, the Archimedean component, equal to d sub k, this d sub k here. A two-dimensional L-adic representation rho of the Galois group of Q, whose local L and epsilon factors, which we briefly talked about a couple videos ago, are in agreement with those of pi sub p for almost all primes p. Okay, so again, so what did we do? We took an arithmetic type representation and we associated to it an L-adic representation rho of the Galois group of Q. And the L and epsilon factors of these two representations match for locally for almost all prime indices P, let's say. Okay. And Carriol's hard theorem essentially says that, as a matter of fact, these L and epsilon factors are in agreement for all primes P. And for a proof, we'll look at an overview of the proof of Carriol's theorem, but Carriol's theorem is one of the hardest theorems I can think of used in the proof of Fermat's theorem. It's up there with the trace formula and some other things. But this is just a glimpse into Carriol's theorem. You see, Carriol's theorem sits inside of a much larger framework. Carriol's work is essentially a special case of a much larger theorem that other people had worked on prior to Carriol. And Carriol basically took care of the hardest cases. And this is one of those cases. So you're probably not getting the full effect of what Carriol's theorem says, and you won't for a while, just by looking at this slide. But I sort of wanted to tie in some of the stuff we had talked about today into a theorem that we've seen before and said very little about. Okay, so starting next video, we'll sort of summarize what we've done, what we need to do. Then we're going to do one last thing. I promised you this, we're going to sort of see how a lot of the discussion we've had so far gets generalized by the notion of Langland's functoriality. We'll do that very briefly. Once we've done that, then I promise we'll finally start collecting the results we need to start proving LRC essentially in the solvable odd case that we factor through the Galois group. Okay? And so I will see you all tomorrow, and thanks for watching.